Well, we've seen the generalized binomial coefficients. So we might as well get a generalized binomial theorem to go with them. So here is the statement of the theorem. It's the same thing that you would expect. So for R, any real number, we have, and now it's going to be slightly different, so maybe it's not exactly what you expect. There's no y. 1 plus x to the r is equal to the sum from k from 0 to infinity of r choose k x to the k. Now let's talk about a few different pieces of this that are different. So remember that we had the theorem, maybe I'll put the general, or the regular binomial theorem. So for n, a non-negative integer, right? We had x, or maybe I'll put y first. Y plus x to the n is equal to the sum from k equals 0 to n of n choose k, x to the k, y to the k. So what have we changed? Well, here we have to get rid of this. Nope. We can't have this because, well, if I'd written the binomial theorem down correctly, you would see why. Let's maybe fix that. Okay. So we can't have it because this doesn't make sense when r is going to be something like a half or negative a half. Then we can't really talk about this. So this term doesn't make sense. So we've set y to 1, and that's why we have the 1 over here. Okay. What else has changed? Well, our indexing here goes from 0 to infinity. But our indexing from here could just as easily go to infinity. Because if I have n objects and I try to, or if I have, let's make it specific, if I have 4 objects and I try to choose 8, I cannot do it. So I get 0. So over here, this is actually a polynomial. And it's a polynomial even if I decide to say, okay, let's take it as k greater than or equal to 0. It's still a polynomial because most of those terms are 0. After, when k gets to beyond n, the terms are all 0. This is an infinite series. It really does go on forever. But I'm going to think of it not in terms of the way that we did in Math 126 when we were evaluating power series, because I don't care about issues of convergence. This is just a formal way for me to track these numbers r choose k. So let's do an example to make this a little more concrete. So here's an example. I'm going to let n be a non-negative integer. Okay, and I'm going to set r equal to negative n. So I'm making r negative. And I'm going to let x equal negative y, just to kind of confuse things a little bit more. What do I get when I plug this into the binomial theorem, to the generalized binomial theorem? I get 1 minus y to the minus n is equal to the sum from k greater than or equal to 0 of minus n choose k minus y to the k. And now let's simplify that, because last time we figured out what minus n choose k is. So this is the sum from k greater than or equal to 0. Remember last time we discovered this was actually just choosing with repetition. So it was that repetition coefficient with a negative 1 to the k. And it's n plus k minus 1 by the stars and bars argument. And then I've got minus 1 to the k, y to the k, just breaking that guy out over here. Okay, well, minus 1 to the k times minus 1 to the k is 1. I'm actually going to allow that simplification. So now what do I get? I get the sum from k greater than or equal to 0 of n plus k minus 1 choose k, y to the k. So this generalized binomial theorem kind of gives me the same sort of form that I had for the coefficient. So this is now a polynomial over here, and it gives me the same sort of form that I had when it is a series, but it gives me the same form that I had for the binomial theorem, right? But now I've replaced what I have here with the choosing with repetition. Now I can choose with repetition. But it's the same style of formula. And now I'm going to remind you guys about your Math 126 days. In Math 126, we looked at the power series 1 over 1 minus y is equal to the sum for k greater than or equal to 0 of y to the k. Well, what does that have to do with this? Well, if you look at it, this is the case where n equals 1 over there in the example. So what happens when n equals 1? I get 1 minus y to the negative 1, which is what I have, is equal to the sum k greater than or equal to 0 of n equals 1. 1 plus k minus 1, choose k, y to the k. Well, 1 plus k minus 1, that's just k choose k, which is just 1. So this is a generalization of this famous power series that you played with a lot in 126. We can think of it in this more general form with the generalized binomial theorem. So there are going to be lots of homework problems for you to kind of do these analyses. This gets into a technique in combinatorics called generating functions that we're going to do later in the term. But this makes it a little more concrete. So if you play around with this and get comfortable with that, with these concepts, then generating functions will be pretty easy for you when we get there.